Let's do a couple of examples here of applying that rule we just learned about trapezoidal approximation. Our first example here, we'll do one where we're given the function. In our second example, we'll do one where we are not given the function. We're just given the value of the function at some particular values of x. So, in example 1, we are asked to estimate the area under the function f at x equals root x from x equals 1 to x equals 4 using n equals 4. So n again is our number of intervals. So we've got our function f at x equals root x. We need to know how big our intervals are going to be. Well, again, we just take our range. We're going from 1 to 4, so our range is going to be 4 minus 1, or 3, and we want to divide this into 4 intervals. So each of our intervals is going to have a width of 0.75. Now, if each of our intervals is 0.75, it might be useful, again, just to make a little table and figure out what exactly the boundaries of our intervals are going to be. So we start at 1. Boundary of the ending of our first interval, or our point x1, is going to be 1.75. x2 is going to be, we go up another 0.75. Our next interval, we go up another 0.75 to 3.25. And finally, our endpoint for our area approximation is going to be 4 here. So let's apply our trapezoidal approximation. We know that the area is going to be delta x over 2 all times f at x naught plus 2 times f at x1, okay, and we'll have 2 of all those terms in the middle, all the way up to the very end, where we'll just have 1 of our last term. So our last one is going to be f at 4. Oh, sorry, f at x4. So we'll have 1 x naught term, 2 of everything in between, and 1 sort of term representing our ending. So let's write what this is by putting in the values that we know. We know our delta x is 0.75. Okay, f at x naught is going to be f at 1. We're going to have 2 f at 1.75 plus 2 f at 2.5 plus 2 times f at 3.5, again, plus f at 4. So one first term for our, one term for the start of our area approximation, for the end one for the end of our approximation, and then each term in between, each interval boundary gets multiplied by 2. And then we just need to work out what this is. 0.752 times, well, our function is just root, so root 1 plus 2 root 1.75 plus 2 root 2.5 plus 2 root 3.25 plus root 4. Punching all this stuff into our calculator gives us an approximate value of 4.66. So that would be our estimate for the area under that curve. Second example, we want to use, again, trapezoidal rule on the following data to estimate the area under the curve of the function from y equals 1 to y equals 3.2. And this is a common way of presenting problems on the AP exam. We're used to in our high school courses to being given the function. They want us not just to be able to apply a rule or memorize a rule and sub information in it if we've got an expression. They want us to be able to understand what that trapezoidal rule means so that we can apply it if we're only given selected values. So we are going from 1 to 3.2. Now let's see. I think I'm going to actually change this one a little bit. I'm going to say that rather than going all the way to 3.2, we're just going to go up to 2. Okay? So area under the curve of the function from 1 to 2 using the table, the values that we have tabulated here. It doesn't tell us how many intervals to have. So I think the easiest way to set it up is to just use the intervals that are given in the table here. If we started from here, if this is our starting point, let's see if I can move this table down a little bit here, give us a bit of space. Yeah. So we would take this value here as x naught. We would take this value here as our last value, x equals n. So this would be x1, x2, x3, x4. So instead of x4, we can call this thing x5, and that's going to be our endpoint. How big is our interval then? Obviously, delta x is going to be 0.2. That's how big each one of our intervals are. So we can apply our trapezoidal approximation. We know we need delta x divided by 2 times. We need our function evaluated at our x naught value, so f at 0, plus 2 times f at 1.2, plus 2 times f evaluated at our next boundary here, 1.2, so f at 1.4, plus 2 f at 1.6, plus 2 f at 1.8, plus f at our endpoint 2.0 with no factor of 2 in front of it. So we're going to have 0.2 over 2 times, how do we evaluate this function? Well, we just read the values out of the table. F at 1 is 4.9. Then we'll have 2 times f at 1.2 is 5.4, plus 2 f at 1.4 is 5.8, plus 2 f at 1.6 is 6.2, so 2 times 6.2, plus 2 times f at 1.8 is 6.7, plus, and then f at 2.0 is 7.0. Okay, and then, well, all of this just goes into our calculator, and I think we end up with an estimate of 6.01. So our estimate for the area under the curve is 6.01.